Hello, am I audible? And is my screen visible?
Yes, sir.
Okay, thank you. Hello everyone, welcome to this NPTEL live session for the course Introduction to Machine Learning. My name is Arun Maiti. I'm a PhD scholar in the Department of Computer Science and Engineering at IIT Kharagpur. So in this live session, we will discuss some practice problems on decision trees. So decision tree is the only topic that was mainly covered in this week, in week 6. So we will discuss some practice problems on decision trees, and if you have any questions or queries regarding this week 6 topic, you can ask me during this session. So we will start solving the practice problems first. So this is the first question. The value of information gain in the following decision tree is, so this is this is the root node, and this is one branch, this is another branch, and entropy at the root node is given, a number of examples, a number of data points at root is given as 30. Similarly, entropy at this left branch is given, and the number of examples coming down to the left branch is also given. Similar information are also given in the right branch, entropy and examples. So from these informations, you have to find out the information gain for this decision. So there is no answer in the chat yet. So to find out information gain, the formula for information gain is that let me denote this root node as, let's say, S, the left node as or left branch as L, and right branch as R. So the information gain due to this split, from S we are getting two branches L and R. This is a split. So information gain due to this split can be written as the entropy of the at the root S minus summation over so summation is not really required. uh, so
So what is LG?
this is IG, information gain. Information gain due to this split is entropy of the at the root S minus the fraction of elements that goes to the left hand side. So if the fraction of element is going to left hand side is denoted by the modulo of R S, and this is modulo of R, this is modulo of, sorry, modulo of A. So this modulo denotes number of elements in that node. So minus, so fraction of elements going to the left hand side
17/30
into entropy of the left branch plus fraction of elements going to the right hand side into entropy of the right branch. So minus in front of this whole summation. So this is the formula for information gain. If the whole set S is split into two branches L and R, then this is the formula to compute the information gain. And if you have more branches, then you have to add such fraction of elements into entropy of that branch additionally. There are only two branches, so only two such elements have been added here. So this entropy of S is given here, which is 0.996, and entropy of L is given here 0.787. Entropy of R is given here 0.391, and this fraction of elements going to left hand side is 17. So 17 elements are there in the left branch out of total 30, so it would be 7 by 30, 17 by 30. Similarly, fraction of elements going to the right branch is 13 by 30. So I have found out each of the components in this information gain equation. We just have to put all these values in and compute the information gain value. So is it understandable? Is there any doubt?
So that
0.38
modulus is for
is the answer.
Can you repeat your question?
A can be the answer, 0.380.
So answer is option A, 0.380. Yes. Is any other doubt?
No, sir.
Okay, moving on to the second question. Which of the following is true for a decision tree? Option A is decision tree is an example of linear classifier. Option B, the entropy of a node typically decreases as we go down a decision tree. The entropy of a set increases with its purity. Option D, an attribute with lower information gain is preferred to an attribute with higher information gain as the root. Hmm. Anaga Chogaonkar says option B. Anantapalli Naga Lakshman Kumar says option C. Okay. Anyone else? Ansela VM says option B. The correct answer is option B. So if we go through each of the options, decision first option is a decision tree is an example of linear classifier, which is not correct because decision tree can model any kind of function, whether it's linear or non-linear. So it's not a linear classifier. It can also create non-linear decision boundaries, so it is not a linear function, a linear classifier. Option B says that the entropy of a node typically decreases as we go down decision tree. So this is correct because if we go down the decision tree, um, so the target variable set becomes more and more pure. So the positive classes and negative classes tend to separate more and more as we go down to the decision tree, and that means that entropy keeps on decreasing as we create more and more branches in the decision tree. So the entropy decreases. So this option is correct. And option C says that the entropy of a set increases with its purity. So entropy of a set is given by this equation pi log pi for each I is the ith class here. So if a for a pure class there is uh, pure set, uh, all the elements in that set belongs to a single class. In that case the entropy would be zero. But in case of an impure set, the entropy is more than zero. It is certainly greater than zero. If the set is impure, that is, it is a mixture of different classes. So this is wrong. And option D says that an attribute with lower information gain is preferred with to an attribute with higher information gain. This is certainly not correct. We always try to find out the attribute with the highest information gain at any node in the decision tree. So this is not correct. So only correct answer is option B.
Sir, as the impurity increases, entropy also increases, sir.
Yes, entropy increases because if you oh, so this is there should be a minus in front of this entropy. This is the entropy formula, minus of summation pi log pi. So if there is only one class in that set, so pi for one class would be 1 and for every other class it would be 0. So it would simply be 1 into log of 1 plus 0 into log of 0, something like that. So all this 0 log of 0 becomes 0, and here 1 into log 1, so log 1 is also 0. So the entropy is 0 in case of a pure set. Entropy is 0, but it, it should be a negative in front of it. So minus of 0 is also 0. So for a pure set the entropy is 0, but for any other set, impure set, that these pi values are not 0 or not 1, so something in between 0 and 1. In that case, this each value, the entropy value would be greater than 0.
Sir, can you explain for option B as well, sir?
So in option B, this can also be explained by this entropy formula. That is, as we go down the decision tree, the classes tend to separate out. Uh, so at the leaf node, at the root node, we have mixture of both the classes, plus and minus, or 1 or 0, whatever you call it. And as we go down the decision tree, at the leaf node, we want to have only one class, isn't it? That's why we are creating more and more branches of the decision tree, so that at each leaf node there will be only one class, so that we can predict the class of a test input. So in the root node, there will be, let's say, there are 5 positive, 5 negative examples. And as we go down the decision tree, in the leaf node we want, let's say, 3 positive only, and some node it will be 3 negative and no other positive, so that we can classify nodes. When for a test node, if the computation reaches this node, there are only positive nodes in that leaf node, so only positive class will be predicted for that test element. So as we go down the decision tree, the set becomes more and more pure. So if it becomes more and more pure, so the entropy certainly decreases. Initially, we start with a mixture of all the classes, and as we go down the decision tree, the set becomes pure and more pure, so that at the leaf node we only have only one class. For each leaf node, we should have only one class in that node.
And what about option D, sir?
Option D.
Yes.
Option D is that, I mean, at any node we want to find out the attribute which has the highest information gain. So it's not that we prefer attribute with lower information gain.
Okay, sir. Okay.
Now question 3. Suppose we use the decision tree model for solving a multi-class classification problem. As we continue building the decision tree with respect to the generalization error of the model, the error due to bias increases, error due to bias decreases, error due to variance increases, error due to variance decreases. So what happens to the bias error and the variance error as we continue building the decision tree from the root to the leaf node? As we add more and more branches in the decision tree, what happens to the bias error and the variance error? So as we increase uh, the depth of the decision tree, as we increase the depth of the decision tree, the decision tree models become more and more complex. So the complexity of the model increases if we increase the number of layers or the depth of the decision tree. So if the model becomes more and more complex, so the bias decreases and the variance increases, because if the complexity of the model is increased, it is more likely to overfit. And if in case of an overfitted model, bias should be low but variance should be high. So the correct answer is bias decreases and variance increases, because as we increase the depth of the decision tree, complexity increases. So
So since it's a multi-class classification, we are considering it as complex, sir.
even if it is only two class classification problem, same. I mean, uh, in case of decision trees, multi-class classification don't have any significant change in the model, whether it's two class or multi-class. But the main thing is that as we continue building the tree, means as we are increasing the depth of the decision tree. So the depth is one. At this point, depth is two. We can even add more depth
So the
to it.
complexity will always increase irrespective of the class, sir.
Yeah, if we continue building the decision tree, complexity would uh, increase. So that's why these pruning techniques are there, so that we cut off at some point where we are satisfied that this tree is enough. We don't need more branching. And if pruning is not done, in that case, decision tree might become very deep. In that case, complexity would be very high and it would be very likely to overfit the training data. So that's why we have those pruning techniques, so that we can restrict the complexity of the decision tree and also decrease the height or depth of the decision tree at some point. So for an overfitted model, bias would be low, variance would be high. So the error due to bias decreases as we go down the decision tree, and bias decreases and variance increases as we increase the depth of the decision tree. Question 4. When building models using decision trees, we essentially split the entire input space using option A is axis parallel hyperrectangles, option B is polynomial curves of order greater than 2, option C is polynomial curves of the same order as the length of the decision tree, option D is none of the above. The correct answer is option A, axis parallel hyperrectangles. So decision tree, as you might have already seen in the video lectures, the decision tree divides the entire input space. Let's say this is the entire input space consisting of only two features, x1 and x2. It splits the input space linearly. So if this is the first linear branching that would happen, after that, let's say this is another branching that happens. So this might be another branching. So basically, um, all these straight lines are axis parallel. All these straight lines are axis parallel, and these are hyper rectangles. Each of these are hyper rectangles. I have shown only in two-dimensional space, but it can happen in any dimensional space. Number of features would increase. In that case, if there are 10 features are there in the data set, so 10-dimensional such hyper rectangles would be there. So all these would be hyper. This is one hyper rectangle. This is another hyper rectangle. This is another hyper rectangle. So the input space is split using axis parallel hyper rectangles. So correct option A is the correct answer here. So each branching is one axis parallel straight line, but there are multiple such branchings happen, so it doesn't become a linear decision boundary. In case of other linear regression and also logistic regression, the decision boundaries are there is only one decision boundary that is linear. In case of decision trees, there are multiple such linear boundaries, so the final decision boundary is not a linear decision boundary, so decision tree is not a linear classifier because of that. Now question 5. In building a decision tree model, to control the size of the tree, we need to control the number of regions. So regions basically means these are regions. This is one region, this is one region, this is one region. So each of these region is one split or represented by one node in the decision tree. So in building a decision tree model, to control the size of the tree, we need to control the number of regions. One approach is to to do this would be to split the tree nodes only if the resultant decrease in the sum of squares exceeds some threshold. For the described method, which among the following are true? So this is some kind of pruning method that we split those nodes in the decision tree where the resultant decrease in the sum of squares exceeds some threshold. Otherwise, we will not split that node any further. We will cut off that branch at that node. For the described model, which among the following are true? Option A says it would in general help restrict the size of the tree. Option B says it has the potential to affect the performance of the resultant regression or classification model. Option C is it is computationally infeasible. So multiple options may be correct in this question. The correct answer is option A and option B. So option A says that it would in general help restrict the size of the trees, which is true. That in this pruning technique we split only in those tree nodes where the resultant decrease in the sum of squares error exceeds some threshold. Otherwise, we will not split that node any further. So using this technique, we can reduce the size of the tree or reduce the depth of the tree. So size of the tree can be decreased using this technique. So this option is correct. But the problem with this method is that it may hamper the performance of the method. That is, uh, if we split each and every node to the point we have only one class in the leaf node, then the resultant the error would be minimum. But in this case we are even though the error would be minimized, it is not exceeding some threshold. That's why we are not splitting it. uh, so it would not be able to reduce the error to the minimum, and in some cases it might affect the performance of the resultant regression or classification model. So option B is also correct because of that. And option C says that it is computationally infeasible, which is not correct. This is very much feasible because we are actually reducing the size of the decision tree, and we are not splitting each and every node in the decision tree. So actually we are saving much more time computationally. We are not splitting every tree, we are splitting those we are not splitting every node, we are splitting only on those nodes which uh, uh, where the sum of the squares error exceeds some threshold. So it is computationally feasible, and it takes lesser time than creating the whole tree. So option A and B are the two correct answers. Now question 6.
So can you show the previous slide, sir? So can you explain the B option once again?
So B is that we are uh, even though we might have reduced the error further, we are not splitting the node because the decrease in the error does not exceed some threshold. So we will not be using this pruning technique. We will not be able to get the lowest error or the minimum error. So it might happen that in some cases the performance of this model would not be very good, because uh, we're pruning the decision tree in those nodes where the this condition is not met. This it is not, even though the error would be minimized if we split that node, it would not, if the decrease in the error does not exceed some threshold. That's why we're not splitting. If we split that, the error would be minimum, but we're not splitting it because we don't want to go further in the decision tree, go any deeper in the decision tree to save time.
So basically, after some point that is the given threshold, it won't hold good, sir. That is what they mean.
No, this threshold is for decrease in the sum of the squares error. Uh, in some cases, it might happen that this pruning technique might not give you a good result because we are not minimizing the error to the lowest. We could have reduced the error further by splitting every node. We are not splitting every node. We are splitting only those nodes where this condition is met. It saves us
So
time.
so
That's why
the
pruning is used.
so after some point, the decrease in error won't be necessary, sir. That is what the given point means.
No, after some point you might not want to split further. Let's say you are after the depth 3, you are not splitting any further. So your tree is of depth 3 only. But if you go deeper down, then your tree might be able to reduce the error further, but you are not going down any further because you want to save time in the computation. So it saves time in the computation, but it may affect the accuracy of the model.
Yes, sir.
Question 6. Consider a dataset with only one attribute, categorical attribute, so values are categorical in that attribute. Suppose there are q unordered values in this attribute. How many possible combinations are required to find the best split point for building the decision tree classifier? There are four options: q, q square, 2 to the power q minus 1, 2 to the power q minus 1, minus 1. So the attribute is categorical. There is only one attribute. That attribute is categorical, and there are q unordered values that that attribute can take. So q distinct values are there in that attribute. Anakacho answer is option D, which is 2 to the power q minus 1 minus 1. Okay. And the decision tree only allows binary split, so only two branches would be there in every branching.
Sir,
Yes.
sir, can I ask the doubt of portal lecture? Yes, sir.
Do you have any doubt regarding this week 6 topic?
The previous to previous week, sir. Week 3, week 4, something like that. The lecture we did.
Okay. After
Sir.
these practice problems, you can ask
Okay,
me.
sir. Okay.
So in this question, basically you have q elements in your set, q unordered values that attribute can take, and you have to make binary splits. How can you divide the q elements into two sets? So in one set it might contain x number of elements, the other set would contain, in that case, q minus x number of elements. So how many ways you can split it like this? So you can have 0 elements here, q elements here, 1 element here, q minus 1 element here, 2 elements here, q minus 2 element in the other set. So this way you can split the whole set of q elements. So the first combination q and 0 in one set and q and in the other set, how many ways you can do that? So it is the qc0 qc0. Similarly in the 1 and q minus 1, this split can happen in how many ways? So qc1, the next one would be qc2, so up to qcq it would happen. So these are the different ways of splitting the decision tree, so splitting this attribute values. So you have to add up all those combinations q01, qc1, qc2, qc0, qc1, qc2 up to qcq. So summation of this is 2 to the power q. So this comes from binomial theorem, 2 to the power q. But out of this 2 to the power q number of ways that you can split these q values into two sets. So this first one qc0 and qcq basically means all the elements in one set, the other set is empty. So these two should be removed. So out of this 2 to the power q, these two, this is 1 and this is also 1. So these two ways of splitting should be removed. So 2 to the power q minus 2. Additionally, qc1 is same as qcq minus 1, because qc1 basically means 1 in one set, q minus 1 in the other set. Qcq minus 1 says the exactly the opposite, q minus 1 in one set, 1 in the other set, because these two are equivalent, these two splits are equivalent. So these two will count only once. So similarly qc2 is, this split is same as qcq minus 2. So basically we have to divide this whole thing divided by 2, because each split has been counted twice because of this. So it would become 2 to the power q minus 1 minus 1. So this is the final output. So option D, 2 to the power q minus 1 minus 1 is the correct answer. Is there any doubt in this question? Okay. So next question. Decision trees can be used for the problems where the attributes are categorical, attributes are numeric valued, attributes are discrete valued in all of the above cases. Ansila VM says option D, Anantapalli Nagalaxman Kumar says option D. The correct answer is option D, that in all of the above cases we can use decision tree. If the attributes are categorical and discrete values, it can be directly applied. If the attribute values are numeric valued, you can discretize the values and then apply decision tree. So in all of the cases, decision tree can be applied. Question 8. In a binary classification problem, out of 30 data points, 12 belong to class 1, 18 belong to class 2. What is the entropy of the dataset? Anantapalli Nagalakshman Kumar says minus 12 by 30 log 2 12 by 30 plus 18 by 30 log base 2 18 by 30. Yes, that is correct. So formula for entropy, as we have discussed previously, is given by pi minus of summation pi log pi base 2. So for each class I, in this case we have two classes, class 1 and class 2. So it would simply be minus of p1 log p1 plus p2 log p2. So P1 is the fraction of elements in class 1. So there are 12 elements out of total 13 class 1, and P2 there are 18 elements out of 30 in class 2. So P2 is 18 by 30. Now you just have to compute this 12 by 30 log base 2 12 by 30 plus 18 by 30 log base 2 18 by 30. And minus would be there in front, so don't forget about this minus, otherwise the answer would become negative. This entropy cannot be negative, and if you compute this it would come out as option A, 0.97.
Sir, similar question is also given in week 6 assignment, sir. Entropy for 50-50 split between two classes, something like that, sir.
Yeah, you have to
So, sir,
basically use
can you
similar,
explain
I
this
mean the
question?
exact data are not there.
The data are not same, but the question
The
is same, sir.
question
Please
is,
explain that question also, sir, if it is possible.
yeah, I cannot explain that question right now. After the deadline is over for that assignment, then I can discuss that question. I mean, you just
Okay,
simply have to use this formula. You simply have to use this formula. And this P1, P2 values you have to decide from the data given in that question. I cannot exactly discuss that question right now.
okay, sir.
Question 9. Consider the following data set. So this is a data set given. There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10 elements are there, or 10 data points are there. And this species, this is the y or the target variable, and these are features x1 x2
Excuse me,
x3.
sir. It's a previous answer.
This was option A, 0.97.
Option. Okay, sir.
So the first attribute species is the target variable y, and the other features green, legs, height, smelly. So these are all input features or input attributes x1 x2 x3 x4. So you have to find out the entropy of the entire data set. Anantapalli Nagalakshman Kumar is option A. Okay. Anyone else? Anagha Jogaonkar says option B, which is 1. Okay, so in this question there are 10 rows, so 10 elements are present in this dataset. 10 data points are present, 10. Size of the dataset is 10, and there are species is the decision attribute or the target attribute. So there are two possible values in species. We can see that this m and h, these are the two possible unique values present in this attribute. So how many elements has this value m? So this is 1 2 3 4 5. So there are 5 m's present, and how many h values are present? 1 2 3 4 5. So 5 h values are present. So p1 is 5 by 10, p2 is also 5 by 10. P1 is basically a fraction of elements in class 1. Let's call m as 1, h as 2. So p2 is also 5 by 10. So basically half, both the probability values are half. So now if you put these values into the entropy equation, minus of half log half base 2 plus half log half, so it would become 1. So correct answer would be, option B, 1. So basically there are 5 m class elements and 5 h class elements. So the probability values are half and half for both the classes. So entropy would be minus of half log base 2 half plus half log base 2 half, and the output would be 1.
No, but for only one column.
I cannot hear you properly. Can you repeat the question?
No, only one column you have seen. No, what about the remaining columns? Why you are not
No,
considering that?
for entropy calculation, you only need the y column or the target variable column, which you want to predict. Other columns are input features; those are not considered for entropy calculation. For entropy, you just need the target variable column where the classes would be
Okay,
written.
okay.
Sir, excuse me, sir. If
Yes.
the table is like that, how to identify the target column, sir?
No, you don't have to identify. In this case, the for every table you will be given which one is the target variable. In this case, the species, I'm signifying species as the target variable. So that would be written in the question.
But here it is not
No, it's
mentioned.
not
Yeah.
evident from this question. We don't understand that species is.
No, basically you don't have to. I have already, when I was explaining the question, I uh, told all of you that species is the target variable. That would be given in the question. I forgot to write that in this question. It would be
Okay,
written
sir.
in the question which variable is the target variable, and you don't need to know which attribute means what. You just need to know which are the input attributes, which is the output attribute. You don't need to know what is meant by species, what is meant by green, what is meant by
No,
legs.
but actually,
Yes,
it is not mentioned which is the output or input attribute. No,
I already told. This is why I've written this is the target variable, or why
no,
I
you have
mentioned.
told, but without no, without telling how we will know. Suppose you
No,
get the you
I told you
mentioned
it
it,
will be written.
but if
It will
you
be written in the question. All it will
no,
always
but
be
in this
written.
question it is not given. No, I'm saying if a similar question comes, then it will not be written in that question.
No, it will always be written. I told you that I forgot to write that species is the
Okay,
target
okay, okay,
variable.
okay, okay, okay,
I told
okay,
it verbally, but it is I forgot to write it in this question. But in any
okay.
data
Then
set,
fine. Then
yeah, in any data set, class variable would always be mentioned in the question. Which one is the class variable?
okay, thanks.
Otherwise, how
Fine, fine.
otherwise how will be able to know which one is the target and which how you have to calculate the entropy? So that would always be mentioned in the question.
Actually, in one of the lectures of professor, they had mentioned that each column they were summing. No, that is not required for that's for cross entropy.
No, that is different. This is for calculating the entropy of the entire data set. But after that, if you want to find out the in the next question for the same data set, the data set is same. In the next question, you have to find out the information gain for each of the attributes. Now, information gain is for the
Okay.
input attributes. In
Okay. Okay.
that,
Okay. Fine.
so for
Thank you.
green, legs, height, smelly. In that case, for every input attribute, you have to find out the information gain, and the attribute with the highest information gain would be considered the root of the decision tree. So this is the question 10
Okay.
for for the same data set. Which attribute will be the root of the decision tree? And you have to use information gain measure to compute it. And so again, this species is the target variable y, and the other attributes green, legs, height, smelly, these are input attributes. So this question would take a lot of time, so I will simply describe the process for calculating the information gain and the root of the decision tree. So there are four input attributes: this green, legs, height, smelly. These are the four input attributes. Now for each of these four input attributes, you have to calculate the information gain due to that attribute. So first, if you consider this attribute green, so green, how many distinct values this attribute green can take? We can see there are only two distinct values, n and y are present. So now you have to find out. So if we split the whole data set using this feature green, so in one side we will have all the elements with green equals n, and in the other side we will have all the elements with green value as y. So when green is n, so these are where green is n. So when green is n, you can see that this is one m, this is another m, and there are four h values. So two m values and four h values when green is n. Now similarly, when green is y, you have to compute how many m classes are there and how many h classes are there. So here you have y values for green. This is one m, this is another m, this is another m, this is one h. So 3m and 1h values are there if green is y. So there will be two branches, n and y. So in the n branch we will have two m classes and four h classes, and in y branch we will have three m classes and one h class. So the information gain formula is that entropy of the whole data set. So let's consider E as the entropy. Entropy of the whole data set, let's say whole S represents the whole data set, minus, so fraction of elements, uh, in the n branch of green, and log Pn, sorry, entropy of that n branch plus fraction of elements in the y branch into entropy of the y branch. So this is the formula for information gain. Now this E of S we have already calculated in the previous question. E of S, that is the entropy of the whole data set, that is 1. So E of S is 1. Now this P of n is fraction of elements going to the n side of the branch, inside of the green attribute. So there are total 6, so it would be 6 by 10. Similarly, this py would be If Pn is 6 by 10, it should be 4 by 10 always. And also we can see that the 4 elements are going to the y side of green. So P and Yn values are calculated. Now you have to compute En and Ey. So En, that is entropy of the n side, entropy of this side. So entropy of n side contains 2 m points, 4 h points. So it would be minus of 2 by 6 log base 2 by 6 plus 4 by 6 log base to 4 by 6. Similarly, Ey would be, Ey is the entropy of the y side, which contains 3m and 1h. So it will be minus of 3 by 4 log base 2 3 by 4 plus 1 by 4 log base 2 3 by 4. That is Ey. So Ey, En, Pn, Py, all the values we have calculated, and this Es value is already calculated in the previous question. We have
1
to
by
put
4
all these values.
log base to 1 by 4, no?
Oh yes, it should be 1 by 4. Yes. Now you have to put all these values into this information gain equation to find out the information gain for the attribute green. Now you have to repeat the same process for information gain for legs, information gain for height, information gain for smelly. All these input attributes, for all these input attributes you have to repeat this same process, and the attribute with the highest information gain will be selected as the root of the decision tree. And if you compute, if my calculations are right, it should be
Green also there are, like green also, actually there is En and Ey. So should we combine those two, or we should take, how we will know green alone, because we are getting only En and Ey now.
En is one branch of the green attribute, Ey is the other branch of the green attribute only, isn't it? Green has two values, N and
So
Y.
how do we combine green alone, like En into probability of En?
This one is the combination. Yeah, this one. Pn, that is fraction of elements in the n side into entropy of n, plus fraction of elements in the y side into entropy of y.
Okay.
Fraction of Pn is fraction of elements in the n side, which is 6 by 10, because 6 elements are in the n side and 4 elements are in the y side. So it would be 6 by 10 and 4 by 10 fractional
Okay,
values.
fine, thanks.
So if you compute these information gain values for each of these 4 attributes, green, legs, height, smelly, not for the target variable attribute, you don't have to compute it for the attribute decision variable species. You have to compute this only for the input attributes. There are 4 input attributes: green, legs, height, smelly, and whichever would have the highest value uh, would be taken as the root. And if my calculations are right, it should be legs 0.4. 0.4 is the information gain value for this.
So after calculating the entropy, we are substituting in the formula, sir.
Yes, so all these values of EY and here EN, all these values you have to put in this information gain expression. So basically for every attribute you have to find out the branches that attribute would create. In this case, green would create 2 branches, N and Y. Now how many elements would go to the N side, how many elements would go to the Y side, and what are the class distributions in each of these branches. In the N side we will have 2m and 4h, in the Y side we will have 3m and 1h. So you have to compute such branchings for each of the attributes to compute this entropy values of each of the branches. So these
So
were the
can you show the
questions.
last slide?
Hmm. All these slides should be uploaded, so you can see all these.
Can you please
Yes.
explain 5?
Question 5.
Yes, please.
Sir, 1 minute, sir. We are only calculating for the green, sir.
Yeah, here I have shown only for the green, but you have to repeat this process for the other attributes as well. Only for the input
And
attributes. Hmm?
after repeating, we need to find the highest suitable value, sir,
Yeah,
among
higher
the first.
attribute with the highest information gain value. So this information gain you have to compute for each of the features, input features. Then attribute with the highest information gain would be the root.
Yes, sir. Thank you, sir.
Yeah, so question 5. Yeah, so question 5 is basically your uh,
Not this, not this, not this. Another one. And now next one. Can you not the six then?
this one,
Six.
this one,
No, the two others one. This one.
this one.
Ah, yes, this one.
Yeah, so as I
Ah, yeah.
mentioned that
Six.
so splits can happen as 0 and q. How many ways to do that? Q C 0. Splits can happen 1 q minus 1. So how many ways to do that? Q C minus 1. So you have to calculate such number of ways to split in such ways. Then you have to add all these values because these are the number of ways you can split that attribute. So that is QC0 plus QC1 plus QC2 up to QCQ. And this value is 2 to the power q that comes
Okay,
from
okay.
binomial theorem. And now this QC0
Mm,
and QC1, these are not really splits. It basically says one split would take 0 elements, the other would take all the elements. So these two are not really splits, so you have to remove
okay.
this. So it becomes 2 to the power q minus 2. Now
Okay.
this split 1 q minus 1 and q minus 1 1, these are basically repeated splits. We are not bothered about the
Yeah.
order. 1 q minus 1 and q minus 1 1 are same. So we are actually each
Okay.
split is actually counted twice in our calculations.
Okay.
So we have to remove those repeated calculations. So twice we have calculated each combination. So it would be divided by 2. So this gives
Okay.
us 2 to the power q minus 1 minus 1.
Okay. Thank you.
Sir, can you
Yes.
find that ninth question? Can you find the initial entropy of the spices, sir?
Yeah, initial
Ninth
entropy is
question.
the entropy
Uh,
of the whole data
we are
set or
found all data set only initial, sir. Initial, if they're
yeah,
asked
the
like that.
entropy is that is basically entropy of the class variable. So species is the class variable. You have to find out the entropy of the species. That would give you the entropy of the entire data set. So there are 5 m values and 5 h values. So the
Sir, suppose
probabilities
a
should be
species,
half half,
Okay.
and then
sir,
you have
suppose
to
if a
use this
species
formula.
column is not given,
Yes.
sir, suppose a species column is not given to the first column, then how we calculate the entropy using
No, I
second
mean
column
whichever
entropy?
column is the target variable or the class variable column, that column you have to consider for calculating the entropy of the entire data set.
Okay, so, or
In
sir,
this case,
if the
I forgot
variety
to
of
write,
data
but
set is
species
more
is
than
the
four,
target variable column. And in the question, in the assignment also, one table is given. I have seen, and there
yes,
some column is designated as the class variable or the target variable that you have to predict. So you have to compute the entropy of that column.
Sir, what is the answer of the 10th question, sir?
So 10th question, legs with information gain 0.4 is the correct answer. You can cross check it later by calculating all the values. If I have done it correctly, it should be legs. So is there any other questions or doubts?
sir, the professor, sir, they had the class has been taken by professors and in NPTEL portal. The sir has taught the subset selection, sir. Why we use subset selection, sir? basic need of
So
search
subset
selection.
selection basically it is a feature selection method where we want to reduce the number of input features so that complexity of the model decreases and time taken by the training process would also decrease.
So it is similar to feature selection.
Yeah, it is basically one kind of feature selection that subset selection there are forward subset selection, backward subset selection, all these methods.
Backward.
So it basically we want to reduce the number of input features. We don't want
So
to
sir,
take
subset
all the features. It might have the input data might have 100 features or more than that. In case of image data, it might have 100,000 pixels or 1 million pixels. Each of the pixels would become features. But we might not want to have all the features in our uh, table. We want to reduce the number of features. So that's why these subset selection feature methods are used to reduce the number of features.
but sir, feature selection is also good, sir. So why the time complexity is also matter.
I didn't get your question. Can you repeat?
Sir, time complexity is also came in subset selection.
Yeah, that is in subset selection method that as we reduce the number of features, time complexity decreases for the model. If we have lesser number of features, all the computations would be lesser. So time complexity will also be lesser in that case. So that's why these methods are used.
Sir, basically subset selection is come in a statistical portion. It is true or not, sir?
Statistical portion means
Statics in machine learning, sir. I am asking, I am not telling, sir. I am asking.
no,
Subset
static portion I don't understand because basically you have to do it before you train the model. So that
yes,
you
sir.
reduce
In
the number
model.
of features. After that you have only a few number of features. Now you train your model with those only those reduced features, so you don't use all the features during the training process.
Yes.
For which algorithm do we use this subset selection?
That is for feature selection method. That was those
No, for
forwards.
all this, even for decision tree, everything we can use.
No, it is before applying the machine learning algorithm. You want to reduce the number of features, then you apply the machine learning algorithm. That can be done with any algorithm. Doesn't really matter for that. The machine
Okay,
learning
okay,
algorithm that
okay,
you use, it is to reduce
okay,
the number of features before you train any model.
okay. Thanks. Fine. Like that, what other steps are there similar to subset selection, like for pre-processing?
Pre-processing, you might want to normalize your data by
Okay,
making the values between only between 0 to 1, which is very useful in case of neural networks, that all the
okay,
feature values are between 0 to 1. That is called data scaling or data normalization. And
okay,
feature engineering or creating new features is also another method. You combine some of
okay,
a few of the features to create a new feature altogether. That might be
okay,
helpful to
okay,
your model. So such steps can
okay,
be applied. Yeah.
okay.
Sir, if we have the feature selection concept, then why we use subset selection, sir? You initially you told feature
No,
selection is
subset
similar to.
selection is one of the feature selection methods
Okay,
which
sir.
has been taught in this class. Other methods might also be there which are not taught in this class. But subset selection is one of the feature selection methods. For example, there are feature reduction methods like PCA, principal component analysis. There also you only take the principal components and you don't take all the features. So it is also a feature reduction method that you reduce the number of features. But there you don't
So is this
exactly.
also called a feature selection? PCA
No,
is also for
that is
feature
feature.
selection.
PCA is basically feature reduction method. You don't take a subset of the features. You create new features in PCA. The principal component directions are new features that you create, but actually you reduce the number of features there. So that's why it's called feature reduction method. In subset
Okay,
selection, original features remain the same. You don't create new features or new component directions. Out of the n features, you take let's say some m number of features from them.
your
PCA, LDA, all these are
Okay,
feature
thank
reduction methods. I couldn't hear you.
Okay, but even for subset selection, actually, even for subset selection, it is going to reduce the number of features, no?
Yeah, it is also going to reduce number of features. This is also feature reduction and also called feature selection. You are basically selecting features which you want to use. But PCA and
When you
LDA,
create, when you mm,
PCA, LDA,
when you
these
create
methods
a
are
new feature,
feature
what is it
reduction.
called? Like feature reduction.
Yeah, feature
When you
reduction
create a new, you call
is
feature engineering,
yeah,
no? Okay,
feature engineering is different. You have all the features, now you create new features from by combining
I
those
got it.
features. But
Mm.
feature reduction is basically reducing the number of features using
Uh,
different
uh,
techniques like PCA,
other than,
LDA.
other than, can you give some examples of feature selection, like subset selection? Any other thing is there?
Any other? I don't exactly remember any other such features, but
Okay, fine.
the
Thanks. Okay.
lasso regularization also works as one of the feature selection methods because it reduces for some of the features the coefficient value is reduced to zero. If the coefficient is zero for some feature, that feature is basically removed. So this is also called one of the feature selection,
Okay.
not exactly feature selection, but I don't exactly remember
Yeah, got it. Okay.
any other feature.
Thanks.
Okay, so if there are no other questions or doubts, we can end this live session now.
So I have doubts something about kernels. How
What?
can we select it and kernels?
Kernels?
There is a question. Yeah, there is a question in previous assignment.
Huh.
Types of kernels are there. How can we select which type of kernel is used and which formula is to be applied?
I have not exactly seen that question. You can post your doubt in the discussion forum, but didn't they post the
There are
solution for?
RBF kernel in the last assignment. One code which we have to write, and that is for RBF kernel.
Yes.
How can we select it and choosing the right kernel, linear
Uh,
kernel, polynomial, and RBF sigmoid?
so I
How
mean,
can we differentiate it and what is the use of that?
so RBF kernel basically can be applied in any problem because it can model any complex function. So generally, what is done is that in case of SVM, you apply RBF kernel uh, always, so that
Yeah.
because it can model any complex function, uh, but you can also try other kernels also to check the accuracy because there is no hard and fast rule that in case of this problem this kernel is better, in case of that problem that
Okay.
kernel is better. So you have to try out different kernels and check whichever gives the best result.
Okay.
But generally RBF can model any complex functions. uh,
Okay.
so RBF can be applied in any problem, and in general it gives really good results.
Okay. Okay. Thank you.
Okay, so thank you everyone for joining. We will meet again next week.
Thank you, sir.
Thank you.
Yeah. Thank you, sir.